In this video, we're going to talk about integration in cylindrical coordinates. So let's draw a quick picture of our cylindrical coordinates. Cylindrical in symbols, we talk about representing a point in 3D with the combination of symbols r, theta, and z. And visually, if we've got this point here in 3D, z coordinate in cylindrical is the same as the z that we see in rectangular, so it's just our familiar height. And then if we drop our point xyz down, just project it onto the xy plane, then we're talking about the same r and theta as we had in polar coordinates. So r represents the two-dimensional distance from the origin to our point xy in the xy plane, and theta represents our familiar angle in the xy plane. It's going from the positive x-axis and just rotating counterclockwise towards the positive y-axis. So that's the same direction of rotation as we had in polar coordinates. Now, when we're doing integration in cylindrical coordinates, we just need to be familiar with what dv is going to equal. dv is going to be r dz dr d theta. So there's this correction factor of r that comes up in the dv, and that correction factor comes up for the same reason that it came up in polar coordinates. It has to do with how space is getting distorted when we move from xyz coordinates to r theta z coordinates. We'll actually talk about correction factors in a bit more detail in a later video. Let's set up a triple integral in cylindrical coordinates for the volume bounded by two surfaces, and let's try to draw a picture of our surfaces. So first surface, x squared plus y squared plus z squared equal 12. So that's a sphere of radius root 12. I'm just going to draw that like that. And then second surface, z equal x squared plus y squared. That's a paraboloid, vertex at the origin and opening upwards. So we've got that sort of a shape for our paraboloid. And we're talking about the volume that is bounded between these two surfaces. So this three-dimensional region here that's sitting under the sphere, but above our paraboloid. Well, let's look back at dv for a second that we've got up at the top of the screen. The order of the variables is going to be interesting to us. So dv is going to be r dz dr d theta. We're going to think about the z direction first. So our goal is going to be to slice in the z direction. But remember that we're doing this in cylindrical coordinates. So we want to express everything in terms of z, r, and theta. We don't want to see any x's or y's in our equations. So let's see if we can find the equation of these two surfaces. We've got the sphere and the paraboloid to talk about. The sphere, if we rearrange this for z, we could say z squared equal 12. Now, instead of saying minus x squared minus y squared, I'm going to say minus r squared so that we're getting that into cylindrical. So z squared equals 12 minus r squared. We could then take roots and say z equal plus or minus the square root of 12 minus r squared. If you want something on the upper hemisphere, then you're using the positive root. And if you want the lower hemisphere, then you're using z equal minus root. So in our case, we're going to be using z equal positive root 12 minus r squared. Okay, so that's the equation in cylindrical for our upper hemisphere. And then let's talk about our paraboloid. So paraboloid, I think just to keep this organized, I'll do that a little bit lower down here. So equation in rectangular, z equal x squared plus y squared, but if we move that into cylindrical, z equal r squared. Great. So we're going to be taking slices in the z direction. Let's look at our blue volume here that's shaded in, and just imagine taking a slice in that z direction. So your slice would be starting at the paraboloid and it would be going up to the sphere. So what that tells us is that our z values are going to be ranging from r squared at the bottom to root 12 minus r squared at the top. Okay, so now that we understand what's going on with z, we need to project on the xy plane, and that's where we'll figure out our values of r and theta. So to understand what we're doing here geometrically, I think I'll just draw a rough sketch with a bit less detail. So we've got this paraboloid, on top of that we've got the sphere, and we're trying to find the volume that's enclosed there. So what we're doing is we're looking at the widest point, that is where the two surfaces intersect, and we're actually trying to figure out what points xy do we need to capture there. So we're specifically taking that red disk there and actually projecting that onto the xy plane, and we're trying to capture those sets of points. We're going to call that r. So our goal is to describe r. That's going to give us our limits of integration for the variables radius r and angle theta. Okay, so to get r, it's really coming from the widest point where the two surfaces intersect. So we would normally say z equals z to make that happen. So you could say r squared is the z for the paraboloid, and we want that to equal root 12 minus r squared, which is the z for the sphere. Best way to solve this equation, let's square both sides. R to the fourth equals 12 minus r squared. Could bring everything over to one side. R to the fourth plus r squared minus 12 equals 0. And that's actually a quadratic equation with variable r squared. So let's see if we can factor this in the following way. So we could have r squared plus or minus something times r squared plus or minus something. We want to add up to 1 and multiply to negative 12. So if we did plus 4 and minus 3, that would work. And then if we think about looking at these two factors, setting them equal to 0, r squared plus 4 equals 0 has no real solution. R squared minus 3 equals 0 means r squared is going to equal 3. So r could be either plus or minus root 3, but in the context of radius, we just choose the positive version of that. So we're going with r equal root 3. Okay, so what that does, that describes the radius of the disk that we're seeing in this picture. So that allows us to say that our region r in the xy plane is the region that has radius between 0 and root 3. And because it's a disk, we want to rotate all the way around and say theta is going from 0 to 2 pi. So this is usually the hard part of the problem, is just getting our limits of integration set up for all our variables. So let's just scroll back for a second, see what we said for z. Remember, we figured out that z was going from r squared to root 12 minus r squared. We're going to use that in a second. And we have just now figured out our limits of integration for r and theta. Okay, the other thing I would maybe just refresh our memories about here is that when we're in cylindrical coordinates, we need to know what dv we're using. It's going to be r dz dr d theta. So when we write down our integral, we're typically thinking about it in the order z, r, and then theta. And we've got this correction factor of r that's going to come up every time we write down dv in cylindrical coordinates. Okay, so let's do it. We can say volume, which is what we're looking for, is the triple integral over our solid of dv. And specifically, our dv here is going to be r dz dr d theta, because we're working in cylindrical coordinates. And then we can just plug in our appropriate limits of integration. So we said z was going from r squared to root 12 minus r squared. Our radius going from 0 to root 3, and our theta value going from 0 to 2 pi. So that's our first example of setting up a volume in cylindrical coordinates.